Welcome back to mass transfer operation 2 course. Now we will be discussing on the new topic solid liquid extraction, or we can say this is leaching process. The syllabus is like this: leaching, the single stage operation, and then multi stage operation, and finally we will be discussing about the supercritical fluid extraction followed by equipment for leaching. So, we will be first discussing about the single stage operation. Before that, we will be discussing about the leaching process and how it is different from other separation processes. In the previous chapter, we have learned about this liquid extraction process, or we say this one LLX. There the feed was in the liquid phase, where say carrier solvent was there and extracting say target component was there, and in that feed this extracting solvent was added. Okay. So, due to the solubility difference of the solute in different phases, that is in the carrier solvent and the extracting solvent, the solute was transferred from this carrier phase to the extracting phase. In this solid liquid extraction, we will be discussing the almost similar procedure, except that the in place of this carrier solvent, in case of the solid liquid extraction, there will be one, we can say the solid material, or we can say this one that inert material, okay, or we can say this one the residue, which will be left out after the extraction process. So, we can say this one leaching, that is one solid liquid extraction process, that is the separation process of soluble constituents of a solid material using a suitable solvent. So, inside a solid material, suppose one particular target component is there, which can be solubilized in the particular suitable solvent. Okay. So, there are so many examples, we will be discussing few examples of the solid liquid extraction process. Like this, we can say this one, the one common example is the extraction of oil from oil seeds. Suppose this oil contains mostly say 15 to 20% oil, and the rest amount is this inert, okay, or we say this one the residue. So, that oil content can be extracted using this particular organic solvent, where this oil is solubilized. Okay. And in metallurgical industries, metal extraction is done from the ores. So, here there are some examples like this, we can say, suppose in the metallurgical industries, say suppose the different mixture of hematite, or we can say this one the source of this metal is added, and coke and some limestone, these are added. So, inside this one, we can say this inside this blast furnace. So, the ores are extracted with the help of this coke and say limestone, and then we can say this one, suppose from the outlet this molten iron, that is separated as the product, and we can say this slag, which is we can say this one left out, that is we can say this one as underflow. So, we will be discussing about this whenever we will be discussing about the solid liquid extraction. So, two phases are added in say we can say this one in any extraction unit, or we can say this leaching unit, like say this is one leaching unit. So, two phases like this hematite, coke and limestone, these are added, and say this one it is separated into two different phases like this. One will be this overflow, this is outlet for slag, that is the underflow, and whatever this outlet for molten iron, this is called say overflow. And if we say this essential oil and we can say this volatile oil separation from this say ginger, like this in terms of say 6-gingerol, that is done frequently using this supercritical fluid extraction. So, there actually we get this 6-gingerol, or we can say this some essential oils. Okay. There are so many this one oils, these are recovered using this solid liquid extraction processes. Like also say this one in our daily life, say we generally take this tea, like this tea bag, or we can say this solid matrix is there, or we can say this only tea is there, and we are adding this one in this, we can say this one inside this hot water. Then this from the solid tea, this we can say this one whatever this caffeine that is separated, that is another example of this leaching process. Then we get this green tea. Okay. So, this is we can say this one that is coming out, and whatever is left out, we say this one the whatever the residue is obtained after this leaching process, we say this one as the residue. Okay. So, there are so many like this from fresh coconut also we can get this coconut oil using the similar type of, we can say separation process. This is we can say leaching. So, the basic steps of the leaching, or we can solid liquid extraction, this is almost similar to that of the liquid extraction process, with some amount of modifications or alterations like this. First step is this intimate contact between the solid feed with the solvent. So, here we have this solid is there and we are adding this liquid. So, solid is contacted with the liquid. So, that is why it is solid liquid extraction, and inside this solid, say one target component is there which can be solubilized inside this solvent. Then separation of the extract from the exhausted solid. So, now then we need to say, suppose this is our leaching system, suppose we have this feed and to say we have added their solvent, then we are allowing this system to be separated into two these parts. One we can say this one overflow, then another one is called underflow. Okay. So, we need to separate the extract. This overflow is nothing but this extract, and we can say this one whatever exhausted one is called this underflow. The separation of the solvent, we can say this one, and some entrant solid may be there from the extract, followed by purification of the product, like extraction process. The similar way, recovery of the solvent from the moist solid, just from here we can say this one by pressing, squeezing and drying. So, this one we can recover solvent from both this overflow and underflow, just like extraction process. Say from this extract, this is equivalent to overflow is equivalent to extract, and underflow is equivalent to raffinate. So, liquid extraction also we followed these similar steps. There the last two steps were like this, recovery of the solvents from both the extract and raffinate phases. Okay. Again we are this one discussing the few examples, actually not in detail, but we will be discussing the overall the single stage process and the multiple stages in the this one next few slides. So, suppose the leaching of these ores, that is we can say this oxides, carbonates, sulfides, etc., is a major step in hydrometallurgy. They are leaching of this like copper minerals by sulfuric acid or ammoniacal solution, or we can say the leaching of gold from the ore by sodium cyanide solution, and then we can say this one leaching of low grade nickel ore, like we can say this one, it is called as nickel laterite with sulfuric acid at 250 degrees Celsius and 650 psi, and there actually cobalt is the byproduct. So, in case of this leaching, we will be getting sometimes these useful byproducts, like whenever we have leaching of oil from oil seeds. So, whatever inert actually we will be getting, or we say cake, that is will be the byproduct that will be used as the fertilizer, or we can say for the we can say this cattle also, cattle field, these are actually used as the fodder for those we can say like cows or buffaloes. And another example like this bioleaching of this low grade ores by bacteria, that is we can say this one, these are the newest leaching applications, that is like Thiobacillus ferroxidin, and we can say this one thermophilic species such as we can say this Sulfobacillium or Acidinum are well known. There actually these bacteria, we can say this one dissolve the ores or metal oxides, or say we can say this one from the ores without the application of the chemicals. So, this is we can say this is a new application of the leaching process. and any acid, alkali or solution of complex in chemicals are commonly used for the solubilizing of the target material. So, in that case we can say this one extraction of this target component becomes very high. And another example that we will be discussing in detail like this supercritical fluid extraction, there the target component is efficiently separated using the supercritical fluid like this. We can supercritical carbon dioxide in general to get the we can say this one maximum extraction output this one out of the process. Now, we will be discussing the solid liquid extraction equilibria, that is the similar to that of the liquid liquid equilibria. Like this, here we will be discussing about the concentration of the solute in the clear liquid, we can say this one overflow, that is equivalent to we can say this one extract in the liquid liquid extraction process, and then concentration of the solute in the liquid this one in slurry, or we can say this one in inert material or in the cake, okay, that is termed as the underflow. So, when we say that the system, this solid liquid extraction system has reached its equilibrium, means we can say this one concentration of the solute in the overflow and concentration of the solute in the underflow, that will become same. Okay. And we will be using some notations like this, mass fraction of the species in the overflow will be like y. Say here also we have A, B, C concept, we will be discussing just now, we will be discussing this one, and mass fraction of the species in the slurry, that is will be denoted as x. So, two common techniques actually for separating solid liquid extraction equilibria data are like triangular diagram. In most of the cases we will be using this right triangular diagram we will be using, and another is this Ponchon-Savarit, that is we can say this one solid free basis. It is equivalent to we can say this one just like in case of this liquid liquid equilibrium, that is we can say this one solvent free basis. So, you see these are all almost equivalent actually. We will be discussing whenever we will be solving the problem, we will find that these two processes are almost. So, we can liquid liquid separation process or liquid liquid extraction and solid liquid extraction process wise, these two processes are, or we can say the unit operations are almost similar. Okay. So, the first we can say this one set of these we can say diagram, that is we can say this one triangular diagram, that is we can say this one right triangular diagram, we can say this one equilateral also triangular diagram also we can use. Here you see this, the target solute is placed in x axis and we can say this one solvent is placed in the y axis, and we can say this one just it is also we can say to some extent inverted one compared to the liquid liquid extraction. One can use also C at the tip also means the apex here, and B one can keep B also here. Then otherwise this we can say this one concept wise this is also same. So, whatever the equilibrium data points are there with this underflow and overflow, these are all interrelated with this straight line. One important point is there in case of this leaching process, all the tie lines will move through these 0 0. So, that it has one additional advantage, like whenever we will be drawing any straight line starting from this 0 0 point, means say whenever 100% inert is there, through this whenever we will be drawing any straight line, it will cut both this underflow and overflow, and these are all tie lines. So, that is we can say this on all the tie lines whenever we will be drawing any point like this, and if we extend to 0. So, these all are we can say this tie line. So, we can say this B axis as well as the C axis, these are all also we can say this one tie line values are there. Okay. And say another one is called this Ponchon-Savarit diagram, that are we can say this one, this is solid free basis. Okay, we will be deriving this one how this Z, the Z is similar to that of the extraction process also, and XC and YC this is also similar to that of the leaching process. Here also you see this underflow will be lying almost in the this one what is called the C line, and this the underflow will be like this, it will be following this one, but with the value higher than that 1. Because you see we will be, whenever we will be discussing about Z in the solid free basis, in all the cases for this underflow we will be getting this Z is always greater than 1. We will be getting, we will be just showing this what is the Z value for underflow and overflow, and what is the XC, capital XC and capital YC for this we can see the underflow and overflow. Okay. And so we can say this one, whenever we will be using this Panchon-Savary diagram. So, as it is solid free basis, so the inert has no effect, or we can say whatever k is has no effect on the, we can say this one calculation of the leaching process. And this one first operation, that is we can say the single stage leaching operation. So, suppose this is the leaching process. So, we have added this F with a amount of the, we can say this one mass, that is insoluble, or we can say this is nothing but this inert. So, we can say this one insoluble solid carrier, that is in A. It is equivalent to that of the, we can say this carrier solvent like there in case of this extraction A, and then pure solvent whatever is added, that is we can say this one B. So, here you can say this one pure solvent is added. So, we can say this one B, but we are adding this S amount this pure solvent. We can say this is a leaching solvent, because it does the leaching process. Leaching is nothing but coming out of the solute through from the solid material. Okay. Then we are allowing this process to reach its equilibrium, then it will be converted into two we can say this one phases. One will be the overflow, that is we can say this one, that is our target, where we can say this overflow is V, and one is this underflow, that is we can say this one, that is not required, or we can say this one it will give this byproduct. So, that is we can say this one, that is we can say underflow, or we can say this one leached solid or exhausted solid. But we need to remember that the whatever the target component C is there, say soluble solute, or we can say this one target component will be divided into two parts like this. One part, major part will go to the, we can say overflow, and minor part will come to, or will be carried through this inert insoluble solid, or we can say this one which is inert. So, we cannot completely remove this, we can say this target component this one from this inert, because there will be some amount of association of this target component with the, we can say carrier solid A. Okay. So, we will be doing this simple mass balance, that is very easy. This is feed plus solvent, we can say this one feed contains some amount of, we can say inert material, and that is A amount of inert material plus say some amount of the solute, and the solvent, that solvent may be free of the solute, or maybe sometimes solvent may contain some amount of the target component also, and then it is nothing but the summation of this underflow and overflow, that is the mixture. Okay. So, if we do the solute balance, then we can say F into XCF, then how much amount of the this target component is there, plus this S into YCS. Sometimes it becomes 0, YCS becomes 0 if it is pure solvent. If it is not pure solvent, then YCS will have some values. Then it is nothing but this V into YCS plus L into XCL. So, this is nothing but M into XCM. So, this is this concentration of the solute in the mixture, that is we can say this is a fictitious concentration. So, XCM is nothing but the, we can say this one F XCF plus S into YCS by F plus S, or we can say this V plus L. Okay. So, we can get the solute concentration in the mixture, but in reality we cannot get this one what is called concentration, because it will be separated into two different phases, and we already we have mentioned that sufficient time is given for this either extraction or leaching process to be separated into two different phases, like this in case of this leaching, that is underflow and overflow. In case of this extraction process, that is we can say this extract and raffinate. Okay. So, using this Ponchon-Savary diagram, say now we are converting this one, all this we can see this solid free basis. So, there we can say this underflow, that is leached solid, or we can say this one whatever the cake or exhausted solid will be there, x capital X c will be x c by x b plus x c, and Z L will be x a by x b plus x c. In case of this overflow, that is y c is equal to y c by y b plus y c, and Z v is equal to y a by y b plus y c. So, these are the we can say this one solid free basis, or sometimes we do this one A prime or Z A prime, we use this one where this everything is the solid free basis, like this all the components, or we can say this all the streams are solid free basis, means this one feed, extracting solvent, or we can say this underflow, overflow, then it will be like this. Z F means this whatever the fraction of this we can say this particular material, that is will be in terms of kg solid by kg non solid. Okay. So, in that case we can say the F prime will be kg non solid, means which is solubilized only in the we can say this one in that particular operating condition. So, in that case we can say the F prime plus S prime will be L prime plus B prime, that is nothing but this M prime. So, if we do this solute balance also, that will be F prime into Z F prime plus S prime into Z S prime is equal to L prime Z L prime plus V prime Z V prime is equal to M prime Z M prime. From where we will be getting this Z M prime, here also the concentration of the solute, that is in we can say this is solvent solid free basis, that will be nothing but this F prime Z F prime plus S prime into Z S prime by F prime plus S prime, or we can say this one will be in place of this F prime plus S prime will be L prime plus B prime. Okay. Now, we will be solving a simple problem for the single stage leaching process, very simple problem, and like 1000 kg of the crushed oil sheets, like here 19.5% oil is there and 80.5% meal is there, or we can say this inert or cake is there, that should be extracted with 15,000 kg pure hexane. So, here you see this solute concentration in the hexane the is 0, okay, in a batch extraction vessel. So, we need to calculate the fraction of the oil extracted using this right triangular diagram and Ponchon-Savary diagram. For that, say equilibrium data are given like this one. So, here you see this one, it is expressed in terms of 100 kg, but whenever we will be putting this one in either of these we can say right triangular diagram or Ponchon-Savary, we need to convert this into the corresponding we can say this one x y b y c or capital Y c capital Y b, and with this one we can say this one. So, now it is in the suppose in terms of 100 kg. So, we need to convert this into this we can say the percentage fractions like this. This Y b will be 0.997 and Y c will be 0, and that way we can say this one this whenever Y b is equal to 0.2463, that time this Y c will be 0.7389. So, we need to remember this one also whenever we will be drawing the equilibrium diagram, say in the ternary diagram we need to convert this one. For this we can say whenever we will be putting this one in right triangular diagram, we need to convert this into the fractions only, okay. And whenever we will be putting this one in the Ponchon-Savary, then we need to convert this one in the solid free basis. So, that is very crucial one, but remember that whenever this type of correlations are given, then we can say this one, this Y c is in equilibrium with this Y c and this Y c is in equilibrium with this Y c. So, this is we can say this one, this Y c and X c, these are also equilibrium data points, or we can say these styrene values. And one interesting point that already I mentioned, that in case of this solid liquid extraction, whatever the Y c and X c values are there, it will cross this we can say this 0 point. Okay. So, that is this one, that is the one advantage of this leaching process, and we will be discussing this also in this problem also we will be discussing. Okay. So, we will start solving this one, whatever the we can say data points are given already, we will be first using those, and then we will be placing all these in the right triangular diagram. First we will try with this right triangular diagram, then we will be doing this one for the Ponchon Savarit, or we can say the solid free basis, we will be this one doing that. So, for this whatever the data points are there already, we will need to get this one. Say first feed is given as say 1000 kg, and this solvent is given as 1500 kg. Okay. And then XCF, that is given as 19.5%. So, that will be 0.195, and whereas this YCS, that is in that case it is 0, because it is a pure hexane is given. So, it has no contribution in the towards this we can say this oil extraction. Okay. So, we have this now mixture is equal to we can say F plus S, that is will be like 2500 kg. Okay. Now, we can get this say Xe, say we can say this one M, that will be like F XCF plus S say YCS by A plus S. So, it is coming out as 1000 into 0.195 plus 1500 into 0 divided by 1000 plus 1500. So, it is coming out as very small value 0.078. So, we will be now getting these 3 points like this. So, first we need to locate. So, first step will be locate this F, that is we can say this one F will be like this in the C axis. So, every time actually we put this one F in the C axis, because it contains only A and C. Okay. So, there is no B. Okay. So, because you see A is the we can say this inert, and or we can say this one carrier solid, and C is this we can say this one target component. So, it is we can say this one 19.5. So, we can say F will be like this 0.195 or almost this one here with this y b, that is equal to 0. So, this is coming out here. Okay. And then we have this S. For S, we can say this one X C is 0 or Y C, whatever is that is 0, and the as it is a pure one. So, we can say this one Y B is equal to 1. So, this is nothing but this point. Okay. First, we need to join this S and F. I am not repeating the we can say procedure, or we can say this one design calculation for this this leaching unit, because this is the same as we followed in case of this liquid extraction. So, the same procedure actually we need to follow. So, we need to join this S and F, and now we have this XCM, that is we can say this one 0.078. So, somewhere it will be like this one. So, this one 0.078. So, we will be coming to this point, say that is we can say this one X C is equal to 0.078. So, then we will be getting this M. So, now we have this S and M is like this, a mixture point actually will be like this 0.078, and from here actually we will be getting as this around say y will be like 0.6. So, it is like here. So, we are getting this M here. So, that is placing in this line. So, now, the procedure is very simple like this one. Whenever we have this M, I mentioned that if we just draw a straight line from this 0 point, so then it will be like this. Say if we start from here and if we extend this one through M, will be get it will touch this we can say this overflow line and this underflow line. It will touch as this means if we keep this mixture for a long period of time, then it will be converting into this, we can say this one underflow and overflow. This overflow line means it will be touching at V. So, we can say this one, say we have this, now we can say this one, it is converting, now we have this F, we have S and we have this, we can say this one mixture. Okay. Now, we are drawing this straight line, that is nothing but the, we say I told that this is the tie line for this one, and now it is converting into V and L. So, here this from this diagram actually we will be getting all these composition like this. So, here we can say this one, if we do the component balance here, say like this, say we can say this one V into say Y C V plus we can say this one L into say X C L, that will be nothing but say M into X C M. Okay. So, here this mixture is here actually we say 2500. Okay. So, now we can do one thing, say from here, and so whenever we will be using this graph paper, we will find that the for this L, this we can say we will be getting like this from this graph, or we can say right here from the graph, say Y C will be like this, this value actually is 0.114 and X C, that is obtained as X C, you see this, sorry, this V into Y C, this one, that is obtained as, that is 0.114, and for X C it is obtained as 0.0403. So, this is we can say this one 0.0403. Okay. So, we will be this one getting this one from this graph paper, we will be easily getting this one, and now we will be putting this one in the, we can say this one in the component balance, from where we will be getting both L and V. Okay. So, we will be putting that V into Y C, that is nothing but 0.114, that is we can say this, that is in the overflow line, plus L into 0.0403, that is equivalent to 2500, that is the mixture, into X C is obtained as 0.078, and we know this L is equal to, we can say this one 2500 minus V, that is L is equal to 2500 minus V. So, we will be putting now say V into 0.114 plus 2500 into 0.0403 is equal to say 2500 into 0.078. So, that is coming out as we can say 195. So, from here we will be getting V is equal to 1279 kg, and say L is equal to, we can say 2500 minus 1279. So, it is coming out as 1221 kg. Okay. So, now, so the amount of, we can say this one amount of oil, we can say this one extracted, that is we can say this one V into Y C V, that is coming out as V is equal to 1279 into Y C is already obtained from this graph, that is 0.114 kg. So, it is coming out as 145.8 kg. Okay. So, now we have this dash amount this 145.8 kg oil in the overflow. Okay. So, from here you can say this one the fractional, we can say this one extraction, or we can say this one fraction of oil extracted is equal to, we can say this one, total oil was actually, say we can say this, out of 1000 kg, say 19.5%, that is nothing but 195 kg. So, out of this 195 kg, that 145.8 kg is, we can say this one, recovered, or we can say extracted. So, we can say this one percentage. So, it is coming out as 74.8%. Okay. So, using this single stage operation, this 74.8% oil is extracted from the, we can say this one, extraction, this leaching unit. Okay. So, there 15,000 kg hexane is used for the separation of oil from 1000 kg feed or solid. Okay. Now, we will be discussing with the using this Panchon-Savary diagram. So, I told that, say whenever we will be this one solving this problem using this Panchon-Savary, this is the second we can say this one way of this one solving the problem. So, there we will be converting this overflow and underflow in terms of, we can say this one capital XC, capital YC, and we can say this one Z. So, Z values. So, we will be getting this one. So, now ZL and ZV. So, we will be putting this one, and then we will be getting the underflow and overflow line. And I told that this in case of the underflow, in most of the cases the values will be more than 1. Okay. So, that is, we can say this one, mostly it is the inert materials, or we can say this one where the Kx will be there, or exhaust solid will be there. And this F prime, whatever the feed actually has this, we can say this Z value as more than this one, what is called 4 here in that particular case. Okay. So, now here we will be doing this one in terms of this solid free basis, like this F prime will be like this. So, out of this we can say this one, whatever the, if we this we can say this one, if we remove this inert solid, say we can say this one only 19.5% solubilized solid is there, then it will be like this 1000 into 0.195, that is, we can say this one, it will be 195 kg. So, this is, we can say the F prime is the 195 kg, that is, we can say this one, it is simply nothing but kg non-solid. Okay. So, this is called kg non-solid, and then if we say XC F prime actually, that will be like this, we can say this one mass fraction of solute. So, in feed. So, that will be, we can say this one, whenever it is solute in feed, and that is also in non-solid basis, we can say this one. So, it will be like this 195 by 195. So, that is nothing but say 1, because you see this in total solubilized solid, so how much amount of this one target component is there. So, that is 195 by 195. So, whenever we will be discussing XCF, that is in all the cases it will be like 1. Okay. So, XCF, that is, we can say this one, that will be always like 1. Okay, XCF. And then say ZF prime actually, so that we can say this one, that we derived as kg solid by kg non-solid. So, that is the convention. So, this here actually kg solid is means this out of this 1000 kg, 195 kg is the kg non-solid. So, it is, we can say this one 1000 minus 195, that is coming out at 805. So, it is coming out as, we can say 4.13. That is why you see ZF prime, or say the value Z value of this feed is more than 4. So, in that case, so as we have this one, for this is 4.13. So, that is, we can say this one, and for this whenever we can say this one when XCF is equal to 1, or say capital XC or YC whatever, that is for this case, that is 1. So, this is, we can say this one feed point location is placed here. So, feed point location is placed here now. Now, we can say this YC S prime, that is here you see this one the same problem here, solvent is pure hexane. So, it is we can say this one is equal to say y c s prime, that is 0, and again say z s prime also that will be 0. So, because here this non solid means that is target component that is not present in the we can say this one solvent. So, it is 0 also. Okay. Now, this m prime will be like this, we can say total we can say this one their mixture that will be in the you get solid free basis. So, from this feed we will be getting say 195 kg, and this from the extracting solvent we will be getting the entire one 1500, because this is the pure we can say this one non solid or we can say the solvent. So, it is coming out at 1695 kg. Okay. So, total mixture is like this. So, now we will be say we will be calculating this Z m prime. So, Z m prime is nothing but this from the formula we can say this one f prime and Z f prime plus we can say this one s prime into Z s prime by this f prime plus s prime. Okay. So, it will be like this, f prime is 195 into Z f prime is whatever we got this one 4.13 plus s prime, that is you can say 1500 into Z s prime is equal to 0 divided by 195 plus 1500. Okay. So, it is coming out as 0.475. So, you see this one in this case whatever the mixture is there. So, we have now located this feed point, we have located this S prime, that is nothing but 0, because it does not contain any we can say this one target component. Okay. So, now again we need to join this F prime and S prime as usual. Then we need to get whatever the Z m prime is this one 0.475. So, for that case we will be getting m prime here, and say this one say m prime will be obtained when Z prime will be 0.475, like this, these are actually Z prime. Now, you see this F is located, then S prime is located and m prime is located. Now, you see this one all the tie line values are actually now vertical. Whatever the tie line values actually we will be getting here all will be vertical, because here we have assumed we are expressing this we can say all the underflow and overflow with the solid free basis. That is why all the tie lines are vertical. Okay. So, now we need to this one draw this vertical line through m prime, that is lying in between S prime and F prime. Okay. So, then we will be getting this L prime and we can say this one we will be getting here this V prime. Okay. So, we will be this one now we will be getting this V prime and L prime. Okay. So, there actually we will be getting this Z L prime, that is actually is just above these 2, that is obtained from this graph, actually it is obtained as 2.03, and say Z V prime there is obvious that it will be almost 0, because you see this overflow line whenever we will be converting this into we can say this one solid free basis in the overflow, because there will be no solid, there will be no solid. Okay. That is why it is we can say this always it will be lying in the we can say this one x axis. So, that is why Z V prime will be 0. Okay. Now, we will be doing this one say we can say this XCM, whatever the values actually we are getting this XC value actually for this, that is for all the cases we can say this one for underflow, for overflow, for the mixture, that is XCM value, that is you can say this capital XC m value is nothing but the XC L prime, that is nothing but we can say this one YC V prime, that is coming out as this one, this is 0.115. So, it will be if we use this graph paper, then we will be getting this y prime as 0.115. So, this is we can say 0.115. Okay. So, now we will be doing again we will be doing this component balance like this, we will be getting L prime into you can say this Z L prime plus V prime into Z V prime, that will be coming as M prime into Z M prime. So, here this one we can say this one L prime into Z L prime, that is coming out as Z L prime, that is we can say Z L prime 2.03. So, that is 2.03 plus V prime into Z V prime, that is we got as 0 is equal to M prime, that is M prime is nothing but we can say this one 195 plus 1500 into Z M prime, that we got as 0.475, and here also V prime is equal to this 195 plus 1500, that is we can say this one 1695 minus L prime. So, we can say this one L prime into 2.03 plus 1695 minus L prime into 0, actually it is coming out as 0. So, there is no need of doing this one, and is equal to we can say this 1695 into 0.475. So, from here we are getting this L prime as this 396.6 kg. So, we will be getting this V prime is equal to 1695 minus 396.6, that is coming out at as 1298.4 kg. Okay. So, we can say this one mass of this overflow, that is we can say this one overflow, that is we say V prime, that is 1298.4 kg. Okay. So, we can say this one that fractional oil recovery. So, in percentage if we say will be like this, say V prime into Y C V prime divided by, so whatever the F prime we have into 100. Okay. So, that is coming out as V prime is 1298.4 into Y C prime is equal to say 0.115 divided by say 195, say into 100%. So, it is coming out as 76.6%. So, here we are getting 76.6%, and for that case we got 74.8%. So, we can say this one both are almost same, and if we do this one very precisely, means if we do the calculation in a big graph paper like this, we will be getting the same, we can say this one we will be getting the same fractional recovery. Okay. So, thank you. In the next class we will be discussing about the multi stage of leaching operation.